Okay, I'm going to cover the compiler. It's both a just-in-time and an ahead-of-time compiler merged in one, and there's an assembler too, and an unassembler. It's in the compiler directory. The compiler, the first phase is converting source code to tokens. So like if you have an identifier, the lexical analyzer will put together letters into an identifier. The lexical analyzer will get rid of comments. It will process integers and convert them to a binary internal format. Anyway, so the lexical analyzer is the first. It's kind of like a pipeline, and the lexical analyzer is the first part of the pipe. The parser parses expressions. It's full of calls to lex. That's the lexical analyzer. There it is, looking for an identifier. Anyway, so when the main trick in parsing an expression is operator precedence. And then I'm giving you an overview. Then there's parsing statements. A statement is either an expression, or it's if, for, while. Those are all statements, if, for, while. If you put braces, you can put a statement becomes a block of statements. Anyway, and then after the front end comes well, what we do is when we're parsing, we put together intermediate codes. Most people use a symbol tree, an abstract AST. I use a stack machine intermediate code output. Then after the parsing, you convert it to intermediate codes, and then then you optimize to combine constants together and stuff like that, and merge into complex instructions. And so I have several passes of optimization, and then the final pass is where it converts it to machine code. So you can see here there's a big switch statement, and all those intermediate codes get converted to machine code. Let's go look at an example. I turn on the O trace, that's for the optimizer trace. I'm going to hit, okay, what we're doing is we're adding up the numbers from 1 to n and returning the result. So let's analyze how it's converting this. So when it hits the optimizer, it's been converted by the parser to intermediate codes. So there's an enter to this function. This is a stack machine, so it pushes the base pointer. It pushes an offset of off the base pointer is where a variable goes. Then this add pops the last two and adds them, and then pushes. Then it pushes a 0, and it assigns 0 to the other two, to the result of the add. So that's where it's an assigning. That's an assign statement. This is a marker for end of expression. Now for the for loop, let's see what we're doing. We're pushing the address of I, which is off the base pointer. Then we're adding the base pointer in I. Then we're pushing a 1, and then we're assigning a 1 to I. So this F8 is I, F0 is result. Anyway, so we go on, and then we start getting down to this less or equal branch if 0, and then we have a label. That's what this internal number. Each of these intermediate codes has one number, and then it has a data type. So branch if 0 to this label. Let's see, there's a label D70. So the label branch if 0. So what we're going to do during the different passes is first it has to figure out the type more thoroughly. You know, like when you multiply a float by a integer, you get a float. Well, it has to, in the first few passes, it has to figure out the types. Then it starts converting on pass 3. It's already assigned it's assigned register variables based on how often the offset is used. You see, it sees all those offsets, and it makes a score for each offset to see which one goes and registers. So it is decided on these register variables. Now, if you take the address of a variable, then it can no longer be a register variable because the address of a register is not supported in x86. Anyway, so now it's past 3. It's starting to convert these to complex instructions. This is RISC. You see how these are really simple instructions? This is RISC. And the purpose of the optimizing is to convert to CISC. Now, as it turns out, it doesn't really speed it up much because the processor converts it back to RISC. Isn't that funny? But my optimizing is mandatory because it does some other things than just convert RISC to CISC. So I try to document the stack machine. There's a result and there's data types. So anyway, it starts assigning registers to instead of the stack. It uses registers. RAX is that's the top of the stack. It's kind of what links together each of these intermediate codes. Now, as we get towards the bottom here, the final phases, it's converting to machine code, and I have some rules. Each intermediate code can clobber A, B, C, and D, X, but it can't clobber RSI, RDI. Those are used for register variables. So AX, DX, BX, and CX can be clobbered by each of the intermediate codes. So now let's go take a thorough look at the code now that we know what's going on. So what it has to do is it has to so what it does is it converts the code to an intermediate format that's RISC, and it's a stack machine, and then it converts RISC to CISC and builds up the instructions. It merges together two little instructions into one big instruction, and then in the final phases it starts converting to machine code. And so it turns out that it splices together each of these chunks of machine code to make the final output code. So if you want to see what the compiler is doing, you can otrace will analyze the different optimizing passes. ctrace will just give you the final output. So there's the final output. They've been spliced together into some just-in-time code. Now let's see what it's doing. I always use the base pointer for variables on the stack and accessing arguments. So it's subtracting to create some local storage, but it's going to be using register variables. It saves the variables that you have to save. Now it's starting to XOR, it's starting to initialize the register variables. So it does a two-part. To store a 1, it sets it to 0, and then it does a 1 byte. You can see how I've used 5 bytes to put a 1. If you used the 8 byte, it would be 9 bytes. Anyway, 5 bytes is shorter. I don't care about speed. I just care about pretty code. There it's comparing against n, jump greater. So you're going to have a hard time if you don't know machine code or assembly code. Mine converts straight from the intermediate code to the machine code. It doesn't. There's no stage where it's assembly code. There's incrementing, jumping, and then I use the return that pops the stack. Let's go ahead and analyze. Now that we know what our goal is, let's look at how it does that. So there's a data file with all the opcodes and all the keywords are stored in this data file. The opcode, different addressing modes for the different opcodes are all in here. I hard code when I convert from intermediate code to assembly to machine code. I hard code it. I don't. So you'll see a lot of sometimes I don't hard code it. Mostly I hard code the. I don't make. You can see here it's doing machine. This is machine code for move. There's a one of the library routines is to move. Okay, I'll get into that in a minute. So during the initialization phase, when it first boots, it processes the opcode file and loads it into memory. That's in this That's in this comp init. So it makes some tables. Like there's a table for convert a token to a operator. The lexical analyzer gives you tokens, like token less or equal, and it also gives you identifiers. It'll give you strings. Anyway, so I'm getting ahead of myself. So there's all the intermediate codes. There's a table it processes when it first initializes, and this tells how many arguments on the stack, or how many. You'll see when you're adding, you push. There are 2 arguments on the stack, and 1 result is pushed. So it's got some. This is just to initialize. It tells some information about the intermediate codes. Here it's loading in some data. So during boot, it processes the opcode file, and I use hash tables for keywords, and when it's actually compiling, it puts stuff in a hash table. A hash table is, if you don't know what a hash table is, take an array of 10,000, and if you want to add a variable, then take its letters and add them up, and then look up in the array at the sum of the ASCII, and that's a linked list. You can see. Well, anyway, if you don't know what a hash table is, go find out. So the lexical analyzer is the front of the pipe. In the lexical analyzer, the command prompt is fed into the lexical analyzer. So that's and then when you start including files, it has the main frame structure is called CLEX. This is where when it lexes, it'll store the identifier or it'll store the integer if somebody entered an integer or a float, and it has to keep track of how many include files have been included. So there's a file stack. There's a file stack. It pushes a new file when you do an include. So these clex files are the that's what's keeping track of the file and the position in the file. Let's see, where is the file? There's tokens. Okay, so a file has it's either processing the native documents, or it's processing before the native documents are loaded. It's doing just ASCII. Anyway, so it has to keep track of the current position. When you hit an include, it has to push and start a new position. So the purpose of the lex function, the lex function is the most fundamental function. It converts the stream to tokens. I don't do a preprocessor. Okay, so these tokens start at 100. If it's a multiply or something, then it just returns the ASCII for the operator. We could lex something just to see what it does. Anyway, so I don't have a preprocessor. In my lexical analyzer, I check, and if I hit a pound, then I process a pre-compiler. I do that in my lex. So I'm keeping track of pound define is putting in my table, and I don't do pound define functions. That's not allowed. I don't like pound define functions, preprocessor functions. So so lex is the most fundamental subroutine in a compiler. That's when it's parsing, it'll call lex, and then lex will give you one token. So like if we were lexing this right here, while would be an identifier, and I would return the location in the symbol table of the while. This parenthesis would be returned as a whatever this is, I don't know, 38, 30, I don't know what it is. The parenthesis would be a token. True would be a pound define, and lex would convert it to 1. Then the end parenthesis would be returned. And anyway, so I happen to allow superscripts and subscripts and identifiers, believe it or not. Anyway, so here it's converting a float. I think that's what it's doing. It converts, if you do 0x, it has to convert to hex, or when it's doing a string, it has to convert the backslash tab, backslash quote, backslash, there's binary, lex. Okay, so the lex, there's one function that's called. Now my expression parser has to keep track of operator precedence. I use a state machine when I'm parsing a term. Then I use a state machine. I have to do these are the operators that can go in front. You can put a minus, a unary minus. So it has to be careful of those. And all through the parsing, it's creating these intermediate code entries. Those are those little tiny instructions that we have to optimize and merge. So this has a state machine. The expression parser is a state machine, and okay, well, I think that's pretty self-explanatory. So when you parse an expression, you either when you get a new operator, you either handle it if it's higher precedence, or you postpone it to later if it's lower precedence than the previous operator. So you push on a stack. You'll notice I have a stack somewhere in here. Where's the oops. So there's a stack, this PS stack. That's for the operator when it either postpones an operator or does it right away. So I need a stack data structure to. I push the type of the term or operator, or I push the type or class as well as the. Anyway, so statement parser. So when we parse a statement, we let's say we hit a 4, then we have to go parse the 4. So let's see. So when you parse a 4, you're expecting a parenthesis. I have exceptions, so I can just throw an exception if I don't get a parenthesis after a 4. I skip the parenthesis right there. Then I parse an expression. A for statement has 3 statements. So I parse a statement that's kind of recursive. Then I set a label. I'm going to need a label. Oh, this is for looping backward. This is the loop backward label. We push a intermediate code to mark this label. Then we parse an expression. That's for the that's the continue. The for statement expression is there. Then we either branch backward or we branch over to the end if we don't know where the done is going to be at this point, but we're going to add a label up in the future. We're going to add a label to show the end of the statement. We have to parse in a semicolon. If we're missing the semicolon, we throw an exception. Now it turns out mostly we can do our code in the same order it's coming, but for a for statement you have to rearrange the code because the statement at the end. What are we doing? Basically, what I do is I parse a chunk of code and then I append it at one point. So anyway, that's how it's doing a for statement. Then it now when it optimizes, one of the things it does is simplify constant expressions. If I were to say 1 plus, or let's go back to the let's say I had 1 plus 3 plus 2 plus 1. You can see it put a 10. No, it put a. I'm sorry. It put a 7 in the variable. Now, how did it know that? Well, when it compiles, everybody thinks this is interpreter. This is not. There's no interpreter. There's no byte code. This intermediate code is not really executed. It's sort of executed when you simplify a constant, but that's not a. Some people are just dying to say it's not a compiler. It's a compiler. Fuck you. It's not an interpreter. Anyway, so it simplifies constants in this phase, and it then in phase 3 it figures out which are going to be the register variables, and it starts basically the main thing that happens is during these passes it converts from RISC to CISC, and then on the final passes it converts to machine code. So anyway, you can see the intermediate codes. Now you might see that I have some built-in functions. If you want to build a function into the compiler, it's pretty tricky. First you need in the compiler definition, these are some built-in functions. You're going to need to you add a intermediate code. You have to add a table entry for the intermediate code. If you change the order, that's going to make it really tricky. You have to know what you're doing. I could tell you, but it's too complicated. Anyway, so you add that. This is where you add that. Then during the passes, you have to, if it's a function, mostly you do nothing during the passes when it's simplifying expressions. And then in the final pass, you have to convert it to machine code, and that's up to you. So the optimizer, and then the back end, the pass 789 calls the back end, and the back end has a library. Mainly you add machine code either as 1 byte, 2 bytes, 3 bytes, or 4 bytes of machine code, and you can use some of these library routines. Now I should tell you a little bit more about what's going on. So when it's merging these into a complex instruction, now it's dealing with an immediate. It's not just on the stack. It can be an immediate value. It can be a register variable. It can be a displacement off of. If there's a non-register variable, then you can have a displacement. So the main each item is each argument has a raw type, and then it has you see this TY mask? Let me explain this. All through the back end, you have arguments that are either an immediate or register, or a displacement off a register. This is an indexed relative displacement. This is 64-bit, or it's a stack, system stack. So the entities you're dealing with are one of these types, and then it has it's either a byte, a word, or a float. So when you're doing the back end, you're constantly checking if it's an immediate, you start. This is how the machine. This is the machine code for and branch. So it ands, and then down here it's doing a branch. It either does a short branch or a long branch. During the final phase, it only shrinks during the final 3 passes, it generates machine code, and if a branch is short enough, it uses a short branch, and the rule is you can only shrink during the last few passes. If it expanded, that would break the short jumps. So anyway, so what was I going to say? So you have all of these routines have a type, a register, and a displacement. That's what makes up a item, is a type, a register, and a displacement. And the type is a combination of a TY mask. It's a combination of one of these types, and it's also it's also a size. So for all these back-end routines, you'll see it's checking if the argument is a type, immediate, it has a number, it has a displacement, and a type plus a size is what a type of an argument is. Anyway, so that's my compiler. The final. This is where this is the higher level where it's calling each. It's calling each of the passes in this routine, and then for the final pass, it allocates a chunk of code, a chunk of memory for the code. So once the code size has been figured out, then it allocates off the code heap a chunk of code, and there's where it's allocated off the code heap. It has to do some final adjustments in the last pass. If you have a switch statement, it has to resolve all those jumps, and there's a switch statement array afterward, after the function. So it compiles function by function, and after it's compiled the code, then it inserts all the string constants into this is the pass 789. This is the final pass where it's converting the machine code. After it's finished, it has it stores the string constants, and the jump table data is stored there. So the higher level routine is right here. It's calling all those passes. Then it's simplifying. What is it doing? Simplifying forward jumps. Forwarded jumps, not forward jumps. Anyway, so then this will unassemble, and it returns the code. So you have to know about the symbol table. I told you it has a hash table. Each task has a hash table, and so when it does when it calls a let's compile. How about dir? So it has to it knows where the directory code is in because it looked up in the symbol table, and so all it had to do was do a relative branch. It's actually a lot easier to make a just-in-time compiler than to make it ahead of time. Mine does both. If you look in the compiler, it will generate a binary module if you do ahead of time. Otherwise, it patches up it has to patch all those relative addresses and stuff. Anyway, so that's that.